Hello. We're going to talk about in Chapter 3, average rate of change. So here's a short video kind of going over the note solutions. So you remember average rate of change is slope, the change in y over the change in x, the symbol being m. The formula was y2 minus y1 over x2 minus x1. Well, we're going to look at it a little differently, but really the same thing. So let's say we're trying to find the average rate of change for a function over the interval from a to b. A is where it's starting, b is where it's ending. So instead of saying x1 and y1, we can say a and f of a. So input a, output of a. And then instead of saying x2 and y2, we can say b and output of b. So a is your starting, b is your ending. So it's really the same formula, just using different notation. Now, another way of looking at the same exact thing, instead of saying from starting at a and ending at b, we can say starting at a and then how much time. So for example, if I was going from 2 to 5, that's the same thing as saying from 2 to 3 years later, which is 5. And that formula would be f of a plus h minus f of a over h, where h is how much time and a is your starting. Please understand that all three are the same thing, just looking at it a different way. So we're going to transition from what you remember, y2 minus y1 over x2 minus x1, to f of b minus f of a over b minus a, and then eventually we're going to get to f of a plus h minus f of a over h. So our first example, the following table lists the approximate value of S&P 500 stock market index for a 10-year period from 1995 to 2001. 5 represents 1995. So we have our data from 5 to 11 and our points from 500 to 1200. So if we want to find the average rate of change of the 4-year period from 1996 to 2000 from 6 to 10. So starting at 6, ending at 10. So using the f of b minus f of a over b minus a, we're starting at 6 and we're going to 10. So f of b, b being 10, minus f of a being 6, over b minus a, which is 10 minus 6. So when I have f of 10 minus f of 6, that's a result of 10. So if I go to the table, the output of 10 is 1450, minus the output of 6 is 650, over 10 minus 6, which gives me 800 over 4, which is 200 over 1. So the answer would be the average rate of change from 1996 to 2000 is increasing, because it's positive, 200 points per year. Now remember, how do we get points per year? It's because it's output points over input year. Now I can get the same exact answer using the other formula, f of a plus h minus f of a over h. So it would be f of 6 plus 4 minus f of 6 over 4. Now please understand, it's the same thing. 6 plus 4 is 10, so f of 10 is just what we got last time. F of 10 minus f of 6. It's just looking at it a different way. Instead of starting at 6 and ending at 10, we're starting at 6 and ending 4 years later, which is 10. And you get the same answer, 200 over 1. Another example would be, what is the average rate of change for the 2-year period from 9 to 11? Well, it would be starting at 9, ending at 11, f of 11 minus f of 9 over 11 minus 9. If we go back to the chart, the output of 11 is 200. The output of 9 is 1350. So 1200 minus 1350 over 2, 11 minus 9 is 2, gives you negative 75 over 1. So the average rate of change from 1999 to 2001 is decreasing, because it's negative, 75 points per year. Using the other formula, same answer. F of 9 plus 2, which ends up being f of 11, minus f of 9 over 2, which is h, gives you negative 75 over 1. Understand that both formulas are great, but we're going to start leaning towards the f of a plus h minus f of a over h as we enter some calculus. And then the last example, what was the average rate of change for the S&P over the 3-year period from 1998 to 2001 from period 8 to 11? So we're starting at 8, ending at 11. We look at f of 11 minus f of 8 over 11 minus 8. Comparing it to the other side, f of a, which is 8, plus h, which is 3. 8 plus 3 is 11, minus f of 8 over h, which is 3. So if I look up the output of 11, which is 1200, the output of 8, which is 1200, we get 1200 minus 1200 over 3, which is 0 over 3, which is 0. Same on both sides. So the average rate of change from 1998 to 2001 is no change. And if we drew a little picture, we can see our stock is going up, but then it goes down. And we can see when it's going up, that's what gave it the positive. When it's going down, that's what gave it the negative. And when we have a horizontal line, there's no change there. So we can see it happening. But we're seeing how things change at a given point. Now, we can also do this without the table. So you're based in Indonesia and you monitor the value of the US dollar of a foreign market exchange very closely during an active 5-day period. Suppose you find that the value of $1 US can be well approximated by the function R of t equals 7500 plus 500t minus 100t squared rupees. So it's very important that you understand what is the input, what is the output. Every example needs to start with input, output, input, output. So your input is time in days. Your output is how many rupees. Now we're going to graph this, and I've given you the window, but we're understanding the window. Time in days starts at 0 for 5 days. And looking at the function, we're starting at 7,000 rupees up to 8,600 rupees, and we're going to graph this quadratic function. So I'm going to go to my calculator. I'm going to go turn it on, go to y equals, make sure nothing else is in there, and our function is 7,500 plus 500x minus 100 x squared. Now, we've practiced the calculator, we've practiced quadratics, we're very comfortable with this, I hope. And then we said our window is from 0 to 5 days, counting by ones, and we're starting at 7,000 rupees to 8,600 rupees, counting by 200s, and we've rehearsed, practiced quadratics, so we know that it's A is negative, so it should be a sad face, and we should see the entire graph. And there is our rupees per day, and we're going to find out what it is at a given time period. So, what do you notice? As time increases, the rupees go up and they go down. So what is the average rate of change over the 2-day period from day 1 to day 3? So we're starting at day 1, A is 1, B is 3. So f of 3 minus f of 1 over 3 minus 1. Another way to look at it, f of 1 plus 2 days later, which is still f of 3, minus f of 1 over 2. And we get the same answer, 100 over 1, 100 over 1. So the average rate of change from day 1 to day 3 is increasing 100 rupees per day. So if we look at day 1, we notice it's on the up, and the average rate of change at that point is it's increasing 100 rupees per day. Remember, it's output over input. Now we can do other examples with this. So in 3.2, here's the whole thing worked out if we had done it step by step for day 3 to day 5. So from day 3 to day 5, f of a is 3 plus h is 2 minus r, let's say, of 3 divided by 2. R of 5 gives you 7,500. Now, how did I find this out? 5 is 7,500, 3 is 8,100, and up here 3 is 8,100. Well, we can use the table feature in the calculator. So if I go to the calculator, we're going to hit second window, make sure our table's set up correctly. So second window, we go to change the independent to ask. So when I go to the table, second graph for table, when I plug in 3, it gives me an output of 8,100. When I type in 1, it gives me an output of 7,900. So we can use a calculator, or we can type it in by hand like the example showed, but the calculator helps us a lot. So again, we have to set up our table and then use the table once we have the function in y1. So in this other example, we're going from day 3 to day 5. So 5 gives us 7,500. 3 again gives us 8,100. So we can use the calculator to do that. And we get negative 600 over 2, which is negative 300 over 1. So the 2-day change from day 3 to day 5 is decreasing 300 rupees per day. So if I look at the graph, from 3 to 5 now, it's decreasing. When before, from 1 to 3, it was increasing. 1 to 3 was increasing, day 3 to 5 decreasing. That's what causes those. Now, what if I don't want to know from day 3 to day 5 or day 1 to day 3? I want to know what's happening at day 3 or at day 2 or at a specific day. That's called instantaneous rate of change. Now, instantaneous rate of change is what's happening right now. What's happening right now? Well, the problem with right now is when I go from day 1 to 3, it's a 2-day period. Or day 3 to 5, also 2 days. Or 4 to 5, 1 day. H is 2 or 1. Instantaneous rate of change, H is 0. So we have an issue there. And when H is 0, we know that we can't have 0 in the denominator because it's undefined. So how do we deal with that? Well, we deal with that by our first calculus topic is we're taking the limit as H approaches 0. The limit as H approaches 0. And really what that means is we're just going to get closer and closer to 0 and see what happens. We know we can't plug in 0, but we're going to get closer and closer to 0. Eventually, we'll be able to do another thing called derivative to find out what happens at 0, but first we're going to look at it algebraically. So notice, instantaneous rate of change is also known as derivative. Instantaneous rate of change is derivative, and the idea is we're getting closer and closer to 0 and trying to find out what happens at 0. And we're going to first do it algebraically in the next video, then we're going to do it with the derivative calculus and then check everything in the calculator.